So today we are going to start our first of several talks about transformers. And before we can really get into transformers specifically and understand how they work, we need to have some level of understanding with regards to what mutual inductance is and how it's going to play a role in our systems. Okay. So I'm going to call this generally magnetically coupled circuits. Okay. And the first thing that we are going to talk about is self and mutual inductance. So, what is an inductor? Any of you guys know?
Component that stores energy within a magnetic field.
100% correct, but what does it look like?
We got in 220 or 221 where it's the little round black circle or cylinder with little wires around the
Okay, so I'm going to draw a picture of an inductor here. This is what's commonly referred to as a solenoidal inductor. And it might look something akin to this. So I'm going to have this cylinder here, and this in red is going to be what I'm going to call my core material. And this core material can be a number of different things, okay? And the properties of that material will have a lot to do with how the inductor behaves. But the largest thing that the core material is going to contribute is what's called its permeability, okay? So we'll have some permeability mu that is going to be equal to mu r, the relative permeability, times mu naught, which is the permeability of free space. Okay. We'll talk about this a bit more later on, but effectively that's what our core material is contributing for the most part. And depending on the type of material, that value of mu can either be very small. So if there was effectively, if that core material was air, mu would be exactly equal to mu naught or very, very close to mu naught. Whereas if that core material were a ferromagnetic material like iron or an iron alloy, it could be hundreds to tens of thousands of times larger than the permeability of free space, okay? So around this core material, I'm going to wind a wire. Like so. And I'm drawing these ellipses to represent that this coil of wire might be part of some larger circuit. Okay. So I'm going to say overall that there are n number of turns. Sorry, I misspelled turns in this wire. And the number of turns is also a very important factor for understanding how this is going to behave, okay? So generally speaking, the more number of turns we have, the more inductance this coil of wire is going to exhibit, okay? So it was mentioned a couple of moments ago, completely correctly, that an inductor is a form of energy storage in an electrical circuit, and that energy is stored by the generated magnetic field, okay? So essentially, if I have some current flowing through this wire, which I'm going to call I of t, like so, it will induce a magnetic field in this material. So along the axis, based on the right-hand rule. So how many of you guys are familiar with the right-hand rule? Okay, good deal. So essentially, if our fingers curl around in the direction of the winding of the coil, our thumb is going to give us the direction of the magnetic field, which in this case is going to be up. So there's no such thing as a magnetic monopole. So what we should see is that our magnetic field actually forms closed loops. So along the axis, it's going to be perfectly up like that, but slightly off axis, we might see something like this. And the further away we get from the exact center of that core material, the weaker our field is going to be. Okay. So these bluish lines right here are representing the magnetic field lines that are our energy storage. And I'm going to call these my B field. And I'm going to have some time varying magnetic flux density, B of t, because my current is varying in time. For what it's worth, we might also have some voltage drop across our inductor, V of t, like so. And I've drawn this system such that the current I of t is flowing into the positive polarity terminal of our voltage, so that our inductor is absorbing power and energy. So in this system, the magnetic flux phi b that is passing through the coil is going to be defined as the product of the magnetic flux density B multiplied by the cross-sectional area of the core material A. Okay. So essentially, this area right here is the area A. So that's just the area that is perpendicular to the direction that the magnetic field lines are passing through. And our magnetic flux phi b is just like the total amount of flux that's passing through that particular area. Okay. So I'm going to make a little note here. This is magnetic flux. So we have phi b is equal to B times A, where the units of this is what's called a Weber. Okay. So a Weber, based on our mathematical description here, is going to be whatever the unit of magnetic field is, which happens to be a Tesla, times a square meter, because that's area. But we can also define a Weber if my stylus will write. Hold on, there we go. As simply 1 volt second. So that's our magnetic flux. And since our B field is changing with time, our magnetic flux, phi B, is also going to be changing with time in this particular system, okay? Now, I'm going to define what's called the flux linkage as simply the number of turns multiplied by the magnetic flux. And so flux linkage is a quantity that's simply measured in Webers, because it's just however many turns we have times the number of flux. So it's just a number times flux measured in Webers gives us an answer that is in Webers. Okay. In a linear system, flux linkage and the current that are flowing through our coil are related to each other by what's known as the self-inductance of the coil, okay? So we could say that our flux linkage lambda is going to be equal to L times the current, where this L is our self-inductance, and it is measured in a Henry, where 1 Henry is equal to 1 volt second per ampere, or 1 Weber per amp. And lastly here, according to Faraday's law of electromagnetic induction, we can induce a voltage across our coil, and our voltage V of t is simply going to be the derivative of the flux linkage with respect to time. So if we look at our flux linkage relationship, if L is a constant, then we can pull that out. So we're going to have, let me just write this out explicitly, the derivative of L times I of t is going to look like L times the derivative of current with respect to time, like so. So our current causes some amount of magnetic flux to occur. The ratio of flux linkage to current is known as the inductance, and then the inductance times the derivative of the current gives us the voltage that is induced across the terminals of our coil. So this is self-inductance. Okay. This is something that we see literally every single day. Every current carrying wire, regardless of whether or not it's actually coiled up or not, is going to exhibit some level of inductance, including the wires in our walls and all of that kind of good stuff like that. But it's usually not until we actually coil the wire up in order to concentrate that magnetic field that we actually see any appreciable amount of energy storage, okay? So what happens if I bring a second coil of wire close to a current carrying coil, okay? This is what we're going to see is called mutual inductance. So I'm going to try to draw a simplistic picture here. So on the left-hand side, I'm going to have a simple circuit. I've got some sort of AC excitation, okay? I'm not explicitly saying whether this is a voltage source or a current source because it is literally unimportant. And connected to this, I'm going to have a coil. Something like this. Okay. I'm going to call this guy coil number 1, and it has N1 turns. And because our coil is electrically excited, we are going to observe that some current I1 of t flows through the coil and some voltage V1 of t appears across our coil. Okay. Over here on the right-hand side, I'm going to draw a second coil. I am intentionally trying to depict this as if the coils have different numbers of turns. Okay. So over here on the right-hand side, we're going to have coil number 2, which will have N2 turns. Okay. So for what it's worth, you may have heard this before, and I'm definitely going to use this language in this class often. You might hear me refer to a primary coil and a secondary coil, okay? So the primary coil is the one that I have labeled number 1 here, and the secondary coil is the one that I have labeled number 2 here. Effectively, whenever we have a system like this, whichever coil is connected to our source is going to be referred to as the primary coil. And whichever coil is connected essentially to a load side of the system is going to be called our secondary coil. Once we start talking about transformers specifically, you might also hear me refer to things like the high voltage coil or winding and the low voltage coil or winding. That's just related to the number of turns. And again, doesn't matter which one is the high voltage side, which one is low voltage side, whichever one is connected on the source side, we will consider to be primary. Whichever one is connected on the load side will be our secondary coil. Okay, so I'm going to draw my flux lines again. Okay. So I'm going to have some flux circulating like this, and I'm going to call this particular flux phi 11. So essentially what that subscript means, that is the flux that's generated by coil number 1 that is passing through coil number 1 and is inducing that voltage V1, right? Because without any flux passing through there, we induce no voltage, okay? I'm going to make a note because this can get bothersome. So phi 11 is the flux produced by coil number 1 that is passing through coil number 1. And similarly, I'm going to have some flux over here, and I'm going to call this flux phi 12, where phi 12 is the flux produced by coil number 1. That is passing through coil number 2. So essentially, I have flux that is passing through my second coil. My second coil has some number of turns, N2, so there is going to be some amount of flux linkage. And because that flux linkage is changing, because my flux is changing, I should expect to see a voltage induced across the terminals of coil number 2. So this is, I believe, a pretty darn interesting result, because these two circuits, as they were, are not physically touching each other in any way, shape, or form. Anytime I have a coil in the proximity of another coil that happens to be carrying a current, I will induce a voltage across the terminals of a secondary coil. So this is effectively a wireless form of energy transfer. Now, how many of you all have a phone that is capable of wireless charging? Practically all of us. That is 100% how it works. We energize one coil, and then on the battery of our phone, there is a secondary coil. It's called an NFC antenna, for near field communication antenna. And it is tuned, if I'm remembering correctly, it's been a hot minute since I had to play around with these things, to resonate at a frequency of, I think it's like 13.5 megahertz. And so that 13.5 megahertz means the wavelength is going to be fairly short, which means this phone has to be pretty close to the wireless charger in order for it to actually couple to it and all of that kind of stuff. But the energy that's stored in the coil of the charger gets sent to the coil in your phone, which is then used to charge it. It's also rectified in a whole bunch of other things like that, because this only works in an AC system, and our phone's battery is a DC battery. So we have to convert that AC signal into a DC signal using power electronics and all kinds of good stuff like that. That's an entirely different class. But anyway, so this is something that you guys actually use in your everyday lives, whether or not you realize. This is also how radios work. These coils are effectively antennas, okay? You pick up the signal from the radio station, you filter it, you amplify it, etc. It's all roughly the same thing. So let's see here. So the current I1 is passing through coil 1. It generates a flux that couples with coil 2, and by Faraday's law of induction, a voltage V2 is induced across the coil. So we can mathematically describe this induced voltage V2 as follows, okay? So our voltage V2 is going to be the derivative of the flux linkage for coil 2 with respect to time. So that's going to be the derivative of N2 times phi 1,2 like so. And we know that if we, let me scroll up here just a smidge, right? So I've got N2 times phi 1,2. So I'm using this relationship right here, and I need to figure out essentially how to put this in terms of our current I1, right? So if I set those two relationships for lambda or flux linkage equal to each other, I can see that N times my flux is equal to L times my current, right? So I could say that my flux phi12 is then going to be equal to, let's see, so I'm going to have the derivative with respect to time of N2 multiplied by L1 over N1 times I1. And since N1, N2, and L1 are all constants, I can pull them out, and I'm going to be left with N2 divided by N1 times L1 times the derivative of I1 with respect to time. And I'm going to call this M21 times the derivative of I1 with respect to time, where M21 is the mutual inductance of, coil 2. Induced by current I1 of T. So my mutual inductance is therefore dependent on the number of turns in coil 2, the number of turns in coil 1, and the self-inductance of coil 1, as well as the amount of current that's flowing through our coil. Sorry, the mutual inductance isn't dependent on that amount of current. The voltage is dependent on the current. Okay. So if we were to reverse the roles of our two coils here, so let's say that we excited coil 2 and left coil 1 open circuited, what would we expect to happen? Pretty much. So let's write that out more formally. But yeah, so essentially, if we excite coil number 2 and leave coil 1 open circuited, we are going to wind up inducing a voltage across coil 1 because of the magnetic coupling between the two circuits. And Ricky, you're pretty much 100% right that almost everything is going to be exactly the same, except that we're going to wind up everywhere we see 1, we replace it with 2, and everywhere we see 2, we replace it with 1, which essentially winds up with us flipping that ratio of turns over, but it's also going to mess with some other things really quickly. So just as a quick note here, so if we replace, or excuse me, if we excite we'll find that our voltage V1 is going to be the derivative of phi1 of t, and I'm going to skip those several intermediate steps, and it's going to come out looking like N1 over N2 times L2 di2 by dt is equal to M12 di2 by dt. Now, what's interesting is that in order for energy to be conserved in this system, so let's think about what's happening here, okay? Essentially, coil number one has some amount of energy stored in it because there's current flowing through it, right? We know that the energy stored by an inductor, at least I hope you guys know that the energy stored by an inductor is just 1/2 L times the current squared, okay? So if there's a current flowing through coil one will store some energy. It is going to transfer some portion of its energy over to coil number two. So if we have a conservative system, meaning that the total amount of energy being absorbed by coil one, that's the cap on the amount of energy that can be supplied over to coil two, then what turns out is that these mutual inductances M12 and M21 have to be equal to each other in order for energy to be conserved in the system. So for energy to be conserved, goodness, M21 must equal M12. And so we're now just going to call our mutual inductance M, and we're not going to worry about whether it's between coil two and the current one or between coil one and the current two. Okay, so we're just going to deal with that. All right. So now I want to consider what happens if we excite both of the coils in the system. So I've got my time varying source connected to coil one. And I'm going to denote that coil one has N1 turns. And over here, I'm going to have coil two. Like so. If some current I1 of t is flowing through coil one, then I'm going to have, as previously, some flux here, phi11, as well as some flux that's coupling our two coils together. And I'm going to arbitrarily choose the net direction to be clockwise. Similarly, if I've got some current I2 driving some flux, which I'm going to call phi22 around, what we're going to see essentially is that that flux in the middle area that's coupling those two coils together is going to be dependent on whether phi11 and phi22 are flowing in the same direction or in the opposite direction of each other, okay? And that's going to be dependent on a number of different things, like the direction of the winding and things like that, okay? So I'm leaving that phi in the middle right now kind of ambiguous because I don't know whether or not they're going to add to each other or if they're going to subtract from each other. generating some net flux that's either larger than the individual fluxes or somewhere between the individual fluxes, okay? I hope it's fairly obvious that the current I1 of t will induce some voltage V2 of t across the terminals of coil 2, and similarly, the current I2 of t will induce some voltage V1 of t across the coils, across coil 1. And so what we can do is we can try to figure out what those voltages are going to be. Okay. So I'm going to write my flux linkages here. Okay. So my flux linkage for coil 1 is going to be the self-inductance of coil 1 multiplied by I1 plus the mutual inductance multiplied by current 2. And pretty similarly, the flux linkage for coil 2 is going to be the self-inductance of coil 2 multiplied by I2 plus the mutual inductance between the coils multiplied by I1. So that we can see that those two flux linkages are now dependent on both of the currents in our system, okay? So if we ever have a closed system, so I just want to be clear about this, up here, we saw that our induced voltage V2 was only dependent on our mutual inductance multiplied by our derivative of our current I1, right? I didn't have a self-inductance term because coil 2 is open circuited. So we know that I2 is 0 in this case, right? Now that I've completed the circuit on both sides, my flux linkages are dependent on current 1 and current 2. And what we'll find is that our voltages are going to be dependent on current 1 and current 2, right? So our induced voltages V1 is simply going to be the derivative of flux linkage of coil 1 with respect to time, which will just be L1 times the derivative of I1 plus M times the derivative of I2. And our induced voltage V2 is simply going to be the derivative of flux linkage 2, which will just be L2 times the derivative of I2 plus M times the derivative of I1. So that each of the voltages is composed of a self term due to self-inductance and a mutual term due to mutual inductance. Okay. So a system like this can get pretty confusing pretty quickly. And it all boils down to whether or not those fluxes are going to add together. So that the fluxes that are coupling, if they combine positively and add together, or if they interfere with each other in some way and effectively conflict like subtractively. Okay. So in order to get away from that ambiguity, electrical engineers have come up with what's called a dot convention to help us understand what's going on without having to physically inspect, hey, are these coils wound in the same direction? All of that kind of good stuff, okay? So let's talk about the dot convention now. The goal here is to simplify things. It won't seem like that at first, genuinely, but we will figure out how to apply this in a way that makes sense. And I'm going to try to explain it in the most straightforward way possible because this is something that can be extraordinarily confusing, okay? So I'm going to redraw our system that we just had a moment ago. Here's my excitation source, and then this is going to be the terminals of coil 1. And now I'm just going to draw this guy as if it were an inductor. I'm going to call this inductance L1, and I'm going to put a dot up here. And then on the other side of the circuit, here's my second coil, which has some inductance L2. I'm going to put a dot right here. And then I'm going to denote that these two coils are magnetically coupled to each other by the presence of this arrow. And then I'm going to write the mutual inductance M above that double-headed arrow that's telling us, hey, these coils are coupled. I'm going to define, once again, my current I1 is going to be the current that's flowing into coil 1. And in this particular case, notice that the current I1 is flowing into the dot. And I'm going to define my voltage V1 like this. And notice that the positive polarity terminal of V1 is on the dotted side of that inductance L1. And then the negative polarity terminal is on the undotted side. And I'm going to do something similar for what's going on in coil 2. So I'm going to define my current I2 as flowing into the dot. I'm going to define my voltage V2 as having positive polarity terminal on the dotted side of coil 2. And under this specific case, we could say that V1 is going to be L1 di1 by dt plus M di2 by dt. And similarly, over here, we would have V2 is equal to L2 di2 by dt plus M di1 by dt. So the signs on both the self-induced term and the mutually induced term is dependent on the situation that we have, okay? So I have drawn things so that we should always have plus signs, okay? But I want to effectively make you guys aware of the rules for this because it can be rather confusing, okay? So, rule number 1, okay? the self-induced component of V1 of t is assigned a positive sign if the positive polarity of V1 is at the dotted terminal coil number 1 and I1 enters coil number 1 at the dotted terminal, or, and essentially this or case is just both of those things are reversed, okay? So we could say that the positive polarity of V1 is at the undotted terminal, of coil number 1, and I1 of t enters coil number 1 at the undotted terminal. So I want to be clear here. I'm defining everything. So we're saying the self-induced component of V1 is assigned a plus sign, blah, blah, blah. The exact same rules apply for the self-induced component of V2. So let's just check things really quickly so that we can all make sure that we're understanding what's going on here, okay? So the positive polarity terminal of V1 is at the dotted terminal, okay? So here's my positive polarity terminal for V1, and it is indeed on the dotted side of our coil 1, okay? And our current I1 is flowing into the dot. So that means that that term L1 di1 by dt should indeed have a positive sign. Similarly, the positive polarity terminal of voltage V2 is on the dotted side, and current I2 is flowing into the dot, or the dotted terminal. So the term L2 di2 by dt should also have a positive sign, okay? So those are the rules for the self-induced term. And as we work examples, this will become clearer and clearer, okay? Now we need to come up with the rules for the mutual term. So the mutually induced component of V1 of t is assigned, goodness, a positive sign if, and once again, we're going to have 2 conditions. Okay? the positive polarity of V1 is at the dotted terminal of coil number 1. Make sure that that looks like a good number 1. And I2 of T enters coil number 2 at the dotted terminal. So I want to make an important distinction here, right? So for this check, we need to make sure that the positive polarity terminal of our voltage across coil 1 is at the dotted terminal. But we also need to see that the current that's flowing through coil 2 is entering the dotted terminal of coil 2, right? So we're looking at both sides of the circuit at the same time now for the mutual term. Okay. And then similarly here, we would see that the positive polarity of V1 is at the undotted terminal of coil number 1, and I2 enters coil number 2 at the undotted terminal. So if these criteria are not met, the term gets a negative sign. So I'm going to give you guys a moment to continue writing this stuff down and all that kind of good stuff. And then we're going to shift over to the ICA and see how we can apply this stuff to analyze circuits that contain magnetically coupled coils. And that'll be our lead-in towards transformers. Okay, so we have this gross looking circuit here. That's our first one that we are going to analyze. And I want us to observe a couple of things, right? So this circuit is in the frequency domain, not the time domain, but all of the rules are exactly the same, right? We don't do circuit analysis in the time domain because the math is aggressively difficult. We're going to continue doing all of our circuit analysis in the frequency domain exactly how we've been doing things for the entire rest of this class, okay? So I can see, due to the presence of that double arrow, that J3 ohm coil and that J4 ohm coil are magnetically coupled to each other, and their mutual inductance has an impedance of J1 ohms. I can see by that other arrow that the J3 ohm coil and the J6 ohm coil are magnetically coupled to each other, and the mutual inductance between those two is J2 ohms. Because there's not a double-headed arrow between the J4 ohm coil and the J6 ohm coil, we can only assume that those two are not coupled to each other, right? So only when we see that double-headed arrow connecting the two coils can we say that they are coupled. So despite the fact that all three inductors have dots, we have two pairs of coupled coils. Okay. All right. So how I like to approach these types of circuits is I define the polarity of the voltage drop across my coils that have mutual coupling between them. And then I actually figure out what those voltages are going to be in a symbolic sense. And then I just wind up plugging that into my normal circuit analysis. So I kind of compartmentalize things. I do the hard part first, which is figuring out what the voltages are going to look like with the mutual term and the self term and trying to get all of those signs right. And then I literally just substitute that in as a second step, okay? So in order to make things interesting, I'm going to allow you guys to define the polarities for the voltage drops across these coils, okay? So for the J3 ohm coil, do you want positive polarity on the left or positive polarity on the right, Thomas? Left or right? Right, okay. So I'm going to do this voltage in red, and I'm just going to call this voltage V1. Okay. Let's see. Tucker, do you want the positive polarity on top or on bottom for the J4 ohm coil? There's no wrong answer, just arbitrarily pick one. Top, okay? So I'm going to call this voltage V2. And Brock, would you care for the positive polarity terminal to be on top or bottom for the J6 ohm coil? The bottom, okay? So that's going to be this voltage V3 like so. Now I essentially do mesh analysis whenever I'm analyzing any of these circuits, okay? So I'm going to define two mesh currents. Typically speaking, I always define my mesh currents as flowing clockwise around my loop, but in cases where I have mutual induction, that isn't necessarily the case. So I'm going to once again just let you guys pick, okay? So for the left-hand part of the circuit, do you want our mesh current to flow clockwise or counterclockwise, Ricky? Clockwise, okay? So here is my mesh current flowing clockwise, which I'm going to call I1. And then let's see, Wyvern, would you like for our second mesh current to be flowing clockwise or counterclockwise? Counterclockwise, all right. So that's going to be our second mesh current, I2. Okay, so we have set up the voltages across the terminals of our various magnetically coupled coils, and we have defined the directions for the currents that are flowing through our various magnetically coupled coils, all right? So I'm going to start by trying to define my voltage V1 here, okay? So in order for this first term to be positive, okay, I'm going to need the positive polarity terminal of that voltage V1 to be at the dotted terminal of that J3 ohm inductor, and I need my mesh current I1 to be flowing into the dotted terminal. So is that true? No, right? So the positive polarity terminal is at the dotted terminal, but our mesh current is flowing into the undotted terminal, which means I'm going to have a factor of negative, and now I'm just going to express my frequency domain voltage using Ohm's law. So that's going to be my impedance, J3 ohms, times my mesh current of I1. So before we move on from here, does everybody understand why this is getting a negative sign? Because this is literally the hardest part of this material, is understanding whether or not it should get a plus or a minus. Everything beyond that is doing the exact same shit we've been doing the entire quarter. Yeah. So because the current is flowing into the undotted terminal and the positive polarity terminal is at the dot, is why it gets a minus sign. All right, so now we need to figure out what's going on with our mutual term, okay? So just to make our lives easier. So our mutual inductance is J2 ohms. The current that's flowing through our coupled coil is I2. And so really all we need to do is figure out what the sign is going to be, okay? So let me walk you through the checks, right? So is the positive polarity terminal of the voltage V1 at the dotted terminal of the J3 ohm impedance? Yes, okay. Is the current I2 flowing into the dotted terminal of the J6 ohm impedance? I've seen both of you shake your heads in both directions. So is it a yes or a no? It is a yes. Our mesh current I2 is flowing into the dotted terminal. So this guy is going to get a plus sign. That is our voltage V1. If anybody has any questions, comments, or concerns, I would be more than happy to try to explain it again, but if not, we can move on to V2. So for our voltage V2, I've got a J4 ohm impedance, and I've got a mesh current of I1. Okay. So that's what my self term is going to look like. Should this term get a positive sign or a negative sign? Positive. So it should get a positive sign because the positive polarity terminal of V2 is at the dotted terminal of the J4 ohm inductor, and that current I1 is flowing into the dot. So you're 100% correct. That one should get a plus sign. So I'm literally going to put a plus out here just to remind me that it gets a plus sign. Our mutual term is going to be J1 ohms, and our current is still going to be I1 because that's the current that's flowing into the coupled coil, which is the J3 ohm impedance here. So what should the sign be for our mutual term? Negative. Absolutely right. Because our current I1 is flowing into the undotted terminal of that J3 ohm inductance. Lastly, we need to figure out what our voltage V3 is going to be, okay? So I'm going to put my impedance times my current, so that's J6 ohms, times my current I2, and we need to sort out if that needs a plus sign or a minus sign. So which is it? I disagree.
Negative.
So, well, obviously, if I disagreed with plus sign, it's got to be a negative sign, but let's explain why, right? So the positive polarity terminal is at the undotted terminal of that J6 ohm coil, right? So positive polarity terminal of voltage is on the undotted side. In order for that to get a plus sign, our mesh current I2 needs to also be flowing into the undotted. Since it's flowing into the dot and the voltage polarity is at the undotted, this gets a minus sign. And then we're going to have our mutual inductance of J2 ohms times, in this case, the current that's flowing through the J3 ohm coil, which is I1. What sign should this voltage get? I disagree. So let's check, right? The positive polarity of V3, I'm literally going to draw this out so that we can see it. So the positive polarity of V3 is at the undotted terminal. I1 is flowing into the undotted terminal. So if we have undots on both, it's a plus sign. So I hope, and we'll practice this more today, that I have imparted to you guys that this is genuinely the hardest part of this type of circuit analysis, right? It's so easy to make some small mistake. So what I tend to do, because I am inherently lazy, is if at all possible, meaning that I get to choose the polarity of the terminals and stuff like that, I always put the positive polarity on the dotted terminal, and I always define my mesh currents to be flowing into the dots, if at all possible as well, so that everything gets plus signs. This particular guy right here was designed to be, you can't do that, so that I could force you to practice. Okay. So now that we have those three coil voltages defined, we are just going to go back to applying essentially mesh analysis here. But anywhere that we see one of those voltages that we already have defined, we're just going to plug that in directly, right? So if I were doing mesh analysis, so this is going to be KVL around mesh 1. I'm just following that current I1 around its clockwise path, okay? So the first thing that I see is the negative polarity terminal of my 10-volt source. So I'm going to have negative 10 angle 0 degrees volts. Then I see a 4 ohm resistor. So I'm going to have 4 ohms times I1. Then I see the negative polarity terminal of V1. So I'm just going to do minus V1. And then I see the positive polarity terminal of V2. So I'm going to do plus V2 is equal to 0. And now I'm simply going to substitute those things in, right? So that would look like negative 10 angle 0 degrees volts plus 4 ohms times I1 minus V1. So I'm going to have minus negative. So that's going to look like plus J3 ohms times I1 minus positive. So minus J2 ohms times I2, where just to make it real obvious, this bit right here is just negative V1. And then I'm going to do plus V2. So that's J4 ohms times I1 minus J1 ohms times I1 is equal to 0, where this guy right here is just plus V2. So does anyone have any questions, comments, or concerns about the substitutions that I've done or anything like that? How I wrote my original KVL equation, literally anything. Please, please, please let me know if something isn't making sense. How we defined it in our original circuit diagram up top, right? So as I follow this guy around its clockwise path, the first thing I hit was the negative polarity terminal of the 10-volt source, which is where that negative sign comes from, okay? Then I hit my 4 ohm resistor. Since we didn't define a voltage, I'm just going to assume that it's flowing into the positive polarity terminal, okay? Then we hit the negative polarity terminal of the J3 ohm impedance, which is why I have minus V1. Then we hit the positive polarity terminal of that voltage V2, which is the voltage drop across the J4 ohm impedance. So that's why that guy gets a plus sign. And then I'm back to the node that I started from at the bottom. Now we would do KVL at mesh number 2. And so we're going to follow I2 around its counterclockwise path. So I'm going to choose to say, like, I'm going to ignore that voltage VZ that we're ultimately solving for. I'll get around to that towards the end. But right now, if it's not one of my mesh currents or one of the voltage drops across my coils, I'm just going to pretend those things don't exist until the end. Okay. So the first thing that I see is the negative J2 ohm impedance. So I'm going to have negative J2 ohms times I2. Then I see a 2 ohm resistor. So I'm going to have 2 ohms times I2. And then I see the negative polarity terminal of that voltage V3. So I'm going to do minus V3 is equal to 0. And now I'm simply going to substitute in, right? So that's going to look like minus J2 ohms times I2 plus 2 ohms times I2 minus negative is going to look like plus J6 ohms I2 minus positive is going to look like negative J2 ohms times I1 is equal to 0, where this bit right here is simply minus V3. And I now have a 2-equation, 2 unknown system that I would have to use MathCAD to solve for. So before we get around to potentially doing that, which the hard part of these is actually just setting everything up, let's figure out how we're going to now relate our mesh currents, I1 and I2, to the things that we're ultimately interested in this particular problem, right? So how am I going to find that current IX if I know what my mesh currents are. So I'm looking for this guy right here in terms of my mesh currents. I don't even need to do Ohm's law. It's just I1. They're in the same direction. So down here, I'm just going to put others or other relationships. So we would have IX is simply equal to I1, okay? What about IY? How is that related to I2? Same thing. And then lastly, this voltage VZ, how is it related to I2? So this is where we would actually use Ohm's law. Yeah. So tell me what that's going to look like. So VZ isn't the voltage drop across the total resistance. VZ is just the drop across that minus J2 ohm capacitance. So why would I use the total impedance? Okay. So it's going to be minus J2 ohms times the current, but it needs to be the current that's flowing into the positive polarity terminal. Okay. So what current flows into the positive polarity terminal? Negative I2. So we would say that VZ is going to be negative J2 ohms times negative I2. So do you guys want me to throw this into MathCAD so that we can solve it? Or do you want to accept that we did it correctly and the results of throwing it into MathCAD are what are written down? Essentially, do you want a reminder on how to use MathCAD for this stuff? All right. Let me lower this guy so I can sit down and do this. All righty. So I'm going to put down a solve block because we are solving a system of equations. I really only have two unknown quantities that I am specifically trying to solve for here. That's my mesh current I1 and my mesh current I2. So I'm going to have I1 shift colon 1 control shift P 0 degrees multiply by amps. I think I already earlier in the quarter talked to you about the keyboard shortcuts for the different types of equal signs, how to get the angle operator and all that kind of good stuff. And then here's I2 is 1 angle 0 degrees amps as well. In my constraint section, now I'm going to type out those two equations after I've done my simplifications, everything. So I'm going to do this one on the bottom, the negative 10 angle 0 plus 4 I1, all that kind of good stuff. So let's see. Negative 10 angle 0 degrees volts plus 4 ohms Why is it? Hold on. There we go. Times I1, J3 ohms times I1. Let's see, minus J2 ohms times I2. Plus J4 ohms times I1. And then lastly, minus J1 ohms times I1. Control equals to 0. So that's our first equation. Our second equation, I have minus J2 ohms times I2. Plus 2 ohms times I2. Plus J6 ohms times I2. And then lastly, minus J2 ohms times I1. Control equals to 0. And I'm going to give myself a 2x1 matrix here, where this is how I'm going to solve and save the values of those mesh currents. And I'm going to go to my math formatting tab and put the answer in polar form. And then down here outside of my solve block, I'm now going to do Ix, Iy, and Vz. So Ix was simply I1, Iy was simply I2, and Vz was negative J2 ohms multiplied by negative I2, excuse me. And I don't know why the math formatting didn't stick for everything. So that's what I got, which is decidedly not the answer that I have written down on the assignment sheet. So let's see if we can figure out where our mistake, if there are any, might be. It's always a possibility that I made a mistake earlier. It would be useful if I could see this at the same time as the other thing. So negative 10 angle 0 degrees volts, 4 ohms I1, J3 ohms I1, minus J2 I2, J4 ohms I1, minus J1 times I1 is equal to 0, minus J2 times I2 plus 2 ohms I2, J6 I2. Yes.
Yeah, okay.
What's up?
In the first equation for, we have like the minus V1 section, the minus 2J ohms, I think should be positive.
So the reason why I have, where's my damn cursor at? There we go. So the reason why I have the minus sign right here is because I'm doing minus V1, and that is, so minus this negative turns that term positive, and minus this positive turns that term negative. So are you suggesting that I put the wrong sign there from the mutual inductance? So let's check. Okay. So just to be clear here, let's double check all of these terms for our voltage. Let me make this larger. Okay. So the first term for V1, I said was negative because the positive polarity terminal of the voltage V1 is at the dotted terminal. And our current I1 is flowing into the undotted terminal. So that guy should indeed be negative. For the mutual term, I've got my impedance of J2 ohms, which is my mutual inductance. The current flowing through that coupled coil is the current I2. Let's see, so the positive polarity terminal of V1 is at the dotted terminal, and the current I2 is flowing into the dotted terminal of that J6 ohm inductor. So that guy should indeed have a positive sign. Just double checking the other things here really quickly. So for V2, the positive polarity terminal of V2 is at the dotted terminal of the J4 ohm inductor, and the current I1 is flowing into the dotted terminal. So that's why that first term gets a plus sign. Then we have our mutual inductance. So that's an impedance of J1 ohms times the current I1. Regarding the sign, the positive polarity terminal of V2 is at the dotted terminal of the J4 ohm inductor, and the current I1 is flowing into the undotted terminal of the J3 ohm inductor, so it should have a minus sign on V2. And then for V3, the positive polarity terminal is at the undotted terminal, and the current is flowing into the undotted terminal. So that self term should get a minus sign. Let's see, then I've got J2 ohms, which is my mutual inductance, times the current I1 that's flowing through the coupled J3 ohm coil. Let's see, the positive polarity terminal is at the undotted side of the J6 ohm, and the current I1 is flowing into the undotted terminal. So it looks like I got all of those voltages right. Now let's double check those substitutions, okay? So the minus 10 ohms, the minus 10 volts is fine because it's obviously the negative polarity terminal first. 4 ohms times I1 is fine. Then I have the minus V1. So minus negative J3I1 looks like positive J3I1. Minus positive J2I2 looks like minus J2I2. Now I'm substituting in V2, and that's just a straight substitution. So plus positive J4I1 plus negative J1I1. So that all checks out. KVL for mesh 2, let's see. So we're following that guy around. So I'm going to have negative J2 ohms times I2 plus 2 ohms times I2. And then I'm going to have minus V3. So that's minus negative J6 looks like positive J6 I2. And then I'm going to have minus positive J2 I1 is going to look like negative J2 I1. So the equations that I wrote down appear to be correct. So I believe the issue must be somewhere on when I type stuff into MathCAD, we just have to find it. Or I made a mistake when I solved this previously, which is also a possibility. Ricky, what's up?
The second, loop, when you do the KVL, you go from the bottom right corner up.
Mhm.
Would the negative J2 turn into a positive because it's going from negative, like it's getting the negative first?
So that's where we got that VZ term was negative J2 times negative I2. But in the KVL equation, I'm ignoring that VZ voltage entirely, and I'm just following that current I2 around that path. So I'm saying that I2 sees an impedance of minus J2 ohms, and then it sees an impedance of 2 ohms, and then we hit that minus V3 voltage. So I'm completely ignoring the IY and the VZ, and I'm taking care of that at the very end. So I1 is 1 angle 0, I2 is 1 angle 0, those check out. Negative 10, 4I1, J3 I1, minus J2 I2, J4 I1, minus J1 I1 is equal to 0. That seems to check out. Minus J2 times I2 plus 2 ohms times I2 plus J6 I2 minus J2 I1 is equal to 0. I literally don't see an error here, so I'm going to try to do this a slightly different way and see if the numbers come out the same. So another way that we could potentially do this is to let MathCAD handle all of the substitutions for us. So instead of just saying I1 and I2 are my only variables, now I'm going to say that I1 what's up? Did you find my mistake?
Plus just plus 4.
Where?
That one. Is that gonna be like J?
No, because it's the 4 ohm resistor. So all I'm going to do right now is I'm going to plug in those relationships that we got for V1, V2, V3, as well as our first simple KVL equations to make sure that effectively when I did those substitutions, nothing got messed up there. So V1 was negative J3 ohms times I1. Plus J2 ohms times I2. Oh, and actually that should be a control equal. V2, I have J4 times I1. Minus J1 times I1. Three. That should also be a control equal sign. Minus J6. Let me look at it. Plus J2 times I1. There we go. Now we're doing those two KVL equations. So that's negative 10 plus 4 ohms I1 minus V1. So let's see. Minus V1 plus V2, control equals to 0. And now for my second equation, minus J2 I2 plus 2 ohms I2. So let's see, minus 2J times, goodness, minus V3 is equal to 0. Put my matrix in. So I'm going to solve for V1, then V2, then V3, then I1, then I2. And my X was the same as I1. I got the same answer as before. Y was I2. Same answer as before. And VZ is negative J2 ohms times negative I2. Same answer as before. So it seems like my original solution from when I made this problem a year ago or whatever had an error in it, which happens from time to time because we've solved it essentially two different ways and gotten the exact same result. So I feel pretty strongly that these are the actual correct answers. So it looks like we didn't make a mistake, and I will just need to go hunt through my mistake from last year, which again, this stuff is difficult. And it is very, very easy to make simple mistakes with regards to signs and things like that. So I'm slightly embarrassed that I have the wrong answers on the ICA, but the process is fine, so it is what it is.